I think something really cool about the new definition for Goldilocks zone. Now, a lot of I'm in this book again, this one I'm going to talk about in a little bit, but the establishment science, they have the Goldilocks zone as the star being in the center, and then however far the star is from the host star determines what the Goldilocks zone is based off how hot the center object is. But we all know, that's bogus, because the Goldilocks zone is actually inside of the evolving star itself. So say for instance you have something really hot in the center of the star, and then the outside of it is really cold, like in Jupiter, where the outer atmosphere is like, what, negative 180 to negative 250 or something like that, something really, really cold. So granted, of course, it's not going to be, life isn't going to be in the dead center, and life isn't going to be on the outer regions where it's really, really, really cold. It's going to be moving towards maybe the central surface regions, where the temperature and the pressure and all the elements and molecules are there forming right underneath the surface. And that brings me to what I want to talk about right here, is the secondary structure of proteins. This is what I want to talk about. But it has to do with bonding, because bonding is one of the most important things. If you're going to form proteins, you have to get the elements bonded to other elements to begin with before you can start forming the proteins. You have to have those free radicals, and those free radicals they start combining together inside of the brown dwarf, inside of the atmosphere, to form the beginnings of the amino acids. So here we are, covalent bonds. I'm going to go ahead and read this out to you. The interaction between two atoms arising from the sharing of an electron pair produces a strong interatomic force, the covalent bond. Such forces may be involved in holding two polypeptide chains, meaning two amino acid chains, together, or two sections of a single polypeptide chain in a folded configuration, meaning it's folded like a big sheet of paper. For example, the cross-linking disulfide bond contributed by two half-cysteine residues. Such bonds are not easily broken, but they may be converted to sulhydryl groups by reduction. Reduction and oxidation reactions are very important during, the formation of amino acids inside of the brown dwarf and blue dwarf interiors. Neptune, Uranus, Jupiter, Saturn, those kind of stars. Really evolved stars where they're, cool enough to form these kinds of bonds. Let's see here. Resulting in a separation of the two polypeptide chains, or an unfolding of a single chain. The strength of a covalent bond may be expressed by its dissociation energy, the energy necessary to separate the nuclei from the most stable position or lowest energy level. Table 3.5 lists some values of some common covalent bond energies. See, table 3.5. That's right here. You have the bond, and then you have the energy in kcal per mole. I don't know if you can see that. As well, you have ionic bonds. These are due to charged groups present in the various amino acid side chains, the extent and kind of charge varying with pH. There's another important point. Inside of the interior of the brown dwarf, as it starts forming amino acids in very large scales, you have different changes in pH as you go lower and as you go higher, and the pH can go lower and higher in different levels inside the high atmosphere as you go down into the interior of the brown dwarf. Some are really acidic, some are really basic. But, obviously that changes over time as the interior of that atmosphere evolves. But here it is. They are illustrated in figure 2.9. They interact by mutual attraction or repulsion and affect the conformation of proteins. The energy of electrostatic attraction between oppositely charged groups in aqueous medium is in the order of 5 kcal per mole. Notice how they use aqueous medium here. That's for experimental purposes. when you have life evolving inside of a brown dwarf or blue dwarf, you have gaseous mediums, as well as aqueous mediums, as well as plasmatic mediums, when you form a lot of the beginning radicals to, to form the beginnings of the amino acids. The dissociation of proteins into structural subunits can be affected by changes in pH with a consequent change in charges, meaning as the pH changes, so do the charges change, so does the actual formation of the bonds. So everything is constantly evolving as these things are taking place. It's not something that just, happens and then it's all formed magically. It's a constant change in going back and forth, back and forth, back and forth. So it's constantly stepped as it evolves, and the bonds change. There are frequent examples of dissociation of proteins as the pH of the solution is lowered and negative charges are removed as the carboxyl groups are protonated, and repulsion among positive charges occur. As well, you also have, van der Waals forces and dipole-dipole interactions, as well as hydrogen bonds. And hydrogen bonds play a large part, especially with water, when water begins forming in early stages of stellar evolution. And it's situated towards the lower atmosphere regions of the star. Branch just fell in my car. But yeah, and then you have water, which can facilitate a lot of the aqueous reactions, because water is, very stable. And if you have that at a good temperature, you can facilitate a lot of those reactions taking place. But, yeah, I just wanted to show you guys what I was looking at. Here's a pretty cool diagram of a polypeptide chain to its fullest extended form, together with dimensions. I don't know if you guys can see that, but that's pretty cool. And here you have fundamental dimensions of polypeptide chains is derived from X-ray analysis of amino acids and simple peptides. And the R group is, what can change and what makes the protein, what gives it its actual, name or its actual function is that R group. I'm learning about that as well. And notice how you have parallel structures in these kinds of long chains, and they can all link together like that. And obviously, well, how would this happen? Well, it happens inside of brown dwarfs. It happens inside of all evolving stars. It doesn't happen in asteroids, which then bring the life here, like magically, like a stork bringing a baby, It happens as the star evolves. But and then you have tertiary structure. I'll have to read about that and how people have been figuring out that. And then you have your quaternary structure, which is 4. But yeah, this book has a lot of good information in it. I'm just doing an overview to try to get myself absorbed into what needs to be discussed. And oh wow, this is just like an exothermic reaction, but it includes the enzymes. You have the no enzyme, takes a lot more energy, but then you put the enzyme in there, it would just be like it's just like a catalyst, like platinum. But yeah, I'll go ahead and talk about a lot more of this stuff, but I just don't want to go too in depth because this stuff is really complex. Alright, today is October 7th, 2015.